Hello, I'm Jiok Park from Oracle Labs in Australia. In this talk, I will introduce our work automatically driving JavaScript static analyzers from specifications using meta-level static analysis. This work was conducted with Seungmin An and Seokyeong Ryu at KAIST. Let's start with the background. JavaScript is one of the most popular programming languages, but it is not that easy to correctly understand the possible behaviors of JavaScript programs because of the language's highly dynamic nature and complex semantics. So researchers have presented diverse JavaScript static analyzers to reason about such complex behaviors. Existing JavaScript static analyzers take a compiler-based approach with intermediate representations, shortly IRs. They first compile a JavaScript program into a specific IR program and then analyzes it using a static analyzer for that IR. However, the critical problem of this approach is that it is a manual process, inefficient to handle specification updates. ECMA 262 is the official JavaScript language specification maintained by the ECMA Technical Committee 39, shortly TC39. Let's assume that a new version of ECMA 262 has been released. Then, analyzer developers should read and understand this new specification, and then manually update the compiler in the JavaScript static analyzer. This revision process is tedious, labor-intensive, and error-prone because the language is huge and complex. Since 2015, this problem has been getting worse because TIS39 released the ES6 version in 2015 with a massive update. Moreover, they decided to update the specification every year to quickly adapt users' demands to the specification. So, 7 more versions already have been released since 2015. Because of such frequent releases, unfortunately, all existing JavaScript static analyzers do not or rarely support new language features introduced in ES6 or later versions. To alleviate this problem, we presented a novel interpreter-based approach called meta-level static analysis. Before explaining its concept, I will explain why the interpreter-based approach could resolve this problem. JavaScript is an interpreter-based programming language, and its language specification is also written in an interpreter-based style. In the latest JavaScript language specification, ES12, this abstract algorithm describes how to execute logical OR assignment. It consists of well-organized English sentences as its algorithm steps and treats JavaScript ASTs as values. So it stores ASTs into some variables or passes as arguments to some functions like that. And in AAC 2020, we leveraged this writing style and presented a tool named JSET, which automatically extracts JavaScript definitional interpreters from given language specifications. The extracted definitional interpreter was written in an intermediate representation called IRES. So this IRES function is automatically extracted from the previous abstract algorithm via JSON. So it means that if we can analyze JavaScript programs with JavaScript definitional interpreters, we no longer have to worry about the manual update of the JavaScript static analyzer for new language features. So we presented a meta-level static analysis as an interpreter-based approach to do it. It analyzes the given interpreter using an IR static analyzer with a restricted initial abstract state for a given JavaScript program. Note that it does not directly analyze JavaScript programs, but indirectly analyzes them. Now I will explain how it works with a simple example. Let's assume that we want to analyze this simple JavaScript program using a meta-level static analysis. First, the analyzer parses the program into this JavaScript ASD. Then, it analyzes this IRES function because the target program is a logical assignment, and this function represents the semantics of logical assignment. So if we analyze this IRES function without any restriction, the analysis result represents all the possible behaviors of any logical assignment. But we want to focus on possible behaviors only in the target program. So in the meta-level static analysis, the null analyzer restricts the argument of this function with the AST of the target program like this. Then, with this restriction, the analysis result now represents the analysis result of the target program. So this is the core concept of the meta-level static analysis. We also presented an AST sensitivity to increase the analysis precision. Look at this IRES function. It describes the semantics of identifying references. Even though we already restricted its arguments with the target program, two different ASTs for x and y are merged in the entry of this function. So it does not fully discriminate the JavaScript program point. To limit this problem, we defined AST sensitivity to distinguish calling context using AST. Now let's apply the AST sensitivity in this case. Then calling contexts are divided into two different cases. One case is when the parameter this stores the AST of x, and the other case is when it stores the AST of y. Thus, now we can discriminate the context for all different subtrees of JavaScript programs using AST sensitivity. One interesting point is it works exactly the same as the flow sensitivity for original JavaScript static analysis. It means that AST sensitivity for IRES is the dual concept of flow sensitivity for JavaScript. We also define a dual concept of k-cosine sensitivity for JavaScript by extending the basic AST sensitivity with JavaScript cosine information. So now we can freely configure flow and k-cosine sensitivity for JavaScript by configuring AST sensitivities in the meta-level static analysis. To actualize this technique, we developed a tool named JSaver. As I already explained, we utilized another tool named gset to extract a JavaScript interpreter from a given specification. And JSaver constructs the initial abstract state with extracted IRES functions, but restricted by a given JavaScript program like this. Note that this abstract transfer function is not for JavaScript, but for IRES. To evaluate JSaver, we derived a static analyzer for ES12, the latest version, and compared its analysis result with the state-of-the-art JavaScript static analyzers, TIES and SAFE. The analysis targets are 18.5 thousand JavaScript programs in test 262, which is the official components test suite for JavaScript. First, we check the soundness of each JavaScript static analyzer. For existing static analyzers, we also checked their soundness with Babel. Babel, which is the most widely used JavaScript transpiler, we used it to transpile new language features to ES 5.1 features in each program. As a result, existing analyzers, TIES and SAFE, soundly analyzed only about 26 and 31% of programs respectively. Even after the transpilation, they soundly analyzed only about 37 and 46% of programs respectively. However, our derived static analyzer soundly analyzed all the programs even without using JavaScript transpilers. Then we compare the analysis precision and performance. For a fair comparison, we measure them only for 3.8 thousand programs, soundly analyzed by all the five analyzers. As a result, the derived analyzer had the most precise analysis result, but it was about twice as slow as existing analyzers. So this is the end of the talk. Thank you for listening.